Oh hi! Welcome to this series of videos on thermodynamics. Thermodynamics is an extremely interesting and extremely important subject within physics, but also in other fields of the natural sciences. And that is because thermodynamics is a study of things that connect the different disciplines to each other. Now, this might not be the thing that comes to mind when you think about the word thermodynamics, because unfortunately it comes with some misunderstandings. And I think that in this first video, I'm going to make 4 of them, but in this first video I would just like to dispel some of these misunderstandings, just to get those out of the way, and then we can get started proper. And in the other 3 videos I will explain the 4 laws of thermodynamics, labeled the 0th to the 3rd law for historical reasons. Now, so let's go into some of the misunderstandings. One of them has to do with the word thermo. Thermo might conjure up the idea of things that are hot or things that are cold. So that might give you the impression that thermodynamics is a study of temperature. Now, although that's not completely untrue, it is not completely true either. Thermodynamics is a study of energy and the relationship between energy and, well, the different types that it can go into, for instance, like entropy. And yes, that also means that temperature is part of it. But thermodynamics is not the study of temperature per se, it's a study of energy, and that brings us to the second misconception. Because sometimes when you read books on thermodynamics, for instance, you have this one right here, it's a very good book by the way, you open it up and you see many examples where thermodynamics is applied to things like gases and steam engines. And that might give you the impression that thermodynamics is the study of gases, and again the thermal part might make you think of heat, as in heated gases or something like that. But that is completely far from the truth. It's true that thermodynamics historically was first developed when people started looking at gases during the Industrial Revolution, so in about the 18th and 19th century. So in the course of about 100 years, people started to look at how can we make machines more efficient, steam engines, you put gas in there, you put pressure on it, and how can you make things work, right? How can you make a factory that spews out automobiles, these sorts of things. So thermodynamics was developed indeed in an industrial setting, which back in the day meant gases and this sort of thing. So historically speaking, thermodynamics came out of these sorts of investigations. But then people found out that thermodynamics, the laws that come out of it, these 4 laws actually, apply to every single thing in the universe. It's not just gases, it's not machines. It doesn't matter what it is. It could be something in biology, like a cat or a banana. It could be something in chemistry, like some compound or maybe indeed a gas. It could be something in physics, for instance, quantum mechanics, or even the whole universe as a whole. It turned out that these 4 laws apply to every single thing in the natural world. Not just gases. That happened to be the first thing that where people saw these laws, but the laws applies everywhere. And that's an extremely important thing to take away from this first video. Thermodynamics is the underlying structure of energy and entropy and temperature. And these laws are so general that they apply to every single thing in nature. Doesn't matter if it's biology, chemistry or physics, it applies to everything. Now, that also makes thermodynamics a little bit abstract. Because if it applies to everything, then it's hard to come up with examples that look like everything. So what people typically do is indeed they take examples, and that could be a gas, and then get these laws from these examples. And we will do very similar things in the next couple of videos, but please keep in mind that everything that we're going to derive in the next couple of videos is not going to be contingent on the fact that it happens to be a gas. In fact, in all of my examples that I will show in the videos to come, if you would replace gas by a banana, the laws would still apply, my derivation would still apply, my discussion would still apply. So, if you see me apply things on gases, it's just because I need something to point at. Replace it by a banana, replace it by the universe, replace it by a cat, replace it by a chemical compound, the conclusions will still be exactly the same. Now, this generality of thermodynamics is also why it's such an important field for everybody at MSP to follow. It's not just for the physicists or the chemists or the biologists, it's for everybody. It's also the glue that puts all the disciplines together. We as human beings have a tendency to divide natural science up into these niches. Here's physics, then there's a drawing line, there's chemistry, then there's a drawing line, there's biology. But of course there's only one nature. So we could expect that there must be some laws that are not specific to any of these three areas, because nature doesn't care about the division lines. That's what we human beings made out of it. Whole nature is just one whole thing, so obviously there must be laws that connect everything to each other. That is at its core what thermodynamics is about. Now, in thermodynamics there's 4 laws, and these 4 laws describe everything in the universe. What these laws are, that's what we're going to do in the next couple of videos. In the next video I will talk about the 0th law, historical factoid here. The 0th law was discovered later than the 1st law, but because the 1st law was already given its name, and people found that that 0th law, this new law that they found, was more important than the 1st, they put it in front. But because the 1st law was already called the 1st law, they had no choice but to call it the 0th law. So in the next video I will talk about the 0th law. After the 0th law, the video after that I will talk about the 1st law, and then the video after that I will talk about the 2nd law. That leaves us with one law that's called the 3rd law, which is really just the 4th. The 3rd law I will only briefly touch upon, because it's not, well, it is very important, but it's not extremely important to have a working knowledge of thermodynamics. So we can put this one between brackets. So I will touch upon it when we get there, and I will not say too much about that. Now, one final thing about thermodynamics is that it is about macroscopics. Sometimes when you are a little bit more advanced and you think about thermodynamics, you might have read or seen or be taught that thermodynamics has something to do with particles. In fact, this might be an example that some of you know, the average kinetic energy, so it's called kinetic energy, turns out to be proportional. So let's put an average symbol around this. This just means average. That if you have a whole bunch of particles floating around and I ask you what is the temperature of that gas of particles, then people who already studied a little bit of this might think, well, the temperature is defined as the average kinetic energy of those particles. Yes, that happens to be true for that example. But particles only apply to some systems. In nature, especially in some areas of theoretical physics, you have, well, systems that don't consist of particles at all. That might be strange to you, because you might have taught or have been taught that everything consists of molecules and atoms and this sort of stuff. And if you were then taught a formula like this, there's a number in between, but it doesn't matter for right now. This Boltzmann constant doesn't matter. But if you were taught a formula like this, you might be tempted to think that thermodynamics therefore applies to systems that consist of molecules or atoms, or at least bouncing particles. Though that also is a misunderstanding. Thermodynamics doesn't care about the microscopics. Things like my cat or a banana or the universe indeed consist ultimately of constituents. That could be particles, that could be molecules. It could also be more hypothetical particles, like gravitons or something like that, something exotic. But typically you can break up a system into smaller constituents, and then those constituents have a relationship to each other, and using those relationships you can bring out what the whole system as a whole does. Now, it's true that there's areas of physics that deal with those interactions. Quantum mechanics is a good example, chemistry is a good example, which particles stick together, which parts don't. But thermodynamics doesn't care about the microscopics. To go back one more time to this point that I made about the generality of thermodynamics, that it holds for every single thing, that is exactly because it doesn't care what that thing that you're looking at is made of. A banana is made out of different things than a gas, and a gas is made out of different things than a cat. The cat is made out of different things than the whole universe, yet thermodynamics applies to all these systems. And the reason is exactly because thermodynamics, these 4 laws, don't care about the microscopics. It doesn't matter how the particles in a banana fit together as opposed to the particles in a cat, as opposed to particles in chemistry or to particles in the universe. Thermodynamics applies to it all. So the laws that we're going to look at are macroscopic. You don't need to know anything about the microscopics to get these laws out. Again, this is testament to its generality, because if you don't even have to know what differentiates a banana from a cat, that means that the laws you're going to get are going to hold for all of them. One final misconception about thermodynamics is the word dynamics. Dynamics, the connotation of that word is that it has something to do with time. Dynamics means how are things changing from here to there, the process of changing itself. Now this is for instance true in physics, where you have electrodynamics, which tells you how magnetic fields and electric fields evolve in time from one particular first instance to the second. How does this magnetic field change if I wiggle a magnet around? How will it look later? In Newtonian physics, mechanics, Newton's laws, you have dynamics. If I throw a particle or a pen or a book that direction, or a cat or a banana, how will it fly? It's the dynamics. How will it move from one point in time to the next, and what will the system do? All of this does not apply to thermodynamics. So the word dynamics really is not a very good word. So what does it apply to? Thermodynamics only deals with the beginning of the situation and the end of the situation. Not what happens in between, how you go from the beginning till the end. That has no bearing whatsoever on these laws. These laws are statements about the beginning state and the end state. So, in case of my throwing pen, it would be about that it was in my hand, that's the beginning state, how it fell on the floor, so when it's on the floor, that will be the end state, and how it flew in between, that doesn't matter. Same for chemistry. Thermodynamics doesn't care about, well, I put these two things together, that's the beginning state, and then later on it became that state. Thermodynamics doesn't care about what happened in between, that maybe steam came out or something like that. These sorts of things thermodynamics doesn't care about. So in that sense, the word dynamics is not a good word. It should be called thermostatics or something like that, right? It just cares about the beginning and the end point. Now, to be sure, there are also extensions to thermodynamics that does deal with these intermediate steps, but we're not going to look at those. So let's make that a little bit more clear to wrap up this video. Thermodynamics is the study of energy, temperature, entropy, and related concepts in such a way that they apply to the macroscopics of a system, not about the constituents or the particles or whatever the thing is made out of. And it does it in such a way that whatever comes out is going to be true for all such systems. And final comment, to really wrap everything up, it only cares about the beginning and the end, and not how it got from the beginning to an end. So, having said all that, let's get started proper. We're going to look at the 4 laws in the next few videos. Again, the 3rd law I'll only touch briefly upon. And I will already in this video give you a very short 1-sentence summary of each of those 4 laws. 0th law. It defines the temperature. It is a law that tells you what temperature is. Now, people might be tempted to say at this point, well, I know what temperature is because my body feels temperature every day long. Yes, but in natural sciences, what we'd like to do is have definitions that don't depend on how things feel, but we have to have a rigorous definition, and the 0th law supplies that definition for the concept of temperature. So that's my 1-sentence summary of the 0th law. 1st law. The 1st law, well, typically what you find in popular science books says the conservation of energy. That there is something that is called energy and it cannot be created or destroyed. Although that's not completely untrue, the real meaning of the 1st law is the existence of energy. Energy, again, is a very technical and very rigorously defined concept. So it has to have a rigorous definition. And that's not easy. We use the word energy in everyday speech, and that might give people the false sensation that they sort of know what energy means. But again, in sciences, we'd like to be exact. So the word energy has to be rigorously defined, and that's what the 1st law does. Then there's a 2nd law. This one here. Here's where things become a little bit more abstract. So let me try again a 1-sentence summary. The 2nd law of thermodynamics tells you that there is a maximum amount of energy, this stuff that we defined in the 1st law. There's a maximum amount of energy that you can use to do things. There's always a little bit of energy that cannot be used to do things, and the 2nd law tells you how exactly that is done. By what amount can you take energy and turn it into something else? That's the 2nd law, and for the people a little bit more in the know, we will relate the word entropy to this. So really the 2nd law defines entropy as the amount of energy that cannot be used to make things work or to make things go in nature. Now the third law, again, very brief, it says that there is a 0 point of energy that cannot be reached in a finite number of steps. So you can cool things down. Now what exactly do we mean by cooling things down? Well, we need the concept of temperature, so that we can only define when we have the 0th law. But the third law tells you that if you want to cool things down, make the temperature lower, 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 then you cannot get to the point where all the temperature is gone. You can only do this asymptotically, as in it takes an infinite amount of steps that you have to perform to get there. These 3 laws are the important ones. This one is also important, but not for this introductory series of videos. So, having given you an overview of what thermodynamics is, and having given you an overview, one sentence summary of these 3 laws, let's go into more detail for each of them. So I will invite you now to go to my next video, where we're going to discuss the 0th law of thermodynamics.